The following is a conversation with Dr. Nathan Harshman, professor of physics at American University, specializing in symmetry in quantum systems. My name is Krzysztof Pietroszek, and this is Unorthodox Views, a new podcast on Spotify and YouTube. If you like it, please click the subscribe button, the like button, and if you really enjoyed it, there is a Patreon link in the description. Welcome, Nate. Thank you for agreeing to participate in this podcast. I wanted to start with the following. If we compare let's say, general relativity with quantum mechanics,
sure.
What is the most important difference?
Yeah, so general relativity, first off, I still classify, and most physicists would classify as classical, in that we are talking about particles and fields as opposed to quantum particles and quantum fields. So the uncertainty in classical mechanics, including general relativity, is a completely epistemological uncertainty. It's just we just don't know everything. We can't know everything's position, momentum, because of limitations of observation. But so we have this theory that says that gravity is a force that bends space and time. We can also make classical theories of electromagnetism. And so we put those together, and that describes most things certainly bigger than a virus, really well, to almost any precision we need if it's a simple system. If it's a complex system, or a chaotic system, then that's harder. But yeah, so it really is a world where we can say a particle has a specific trajectory that it follows, where we can say geometry has a specific, the space and time of the universe has a specific shape. And that's a very classical picture. These things have specific answers. In sort of orthodox quantum mechanics, we're talking about measurements. What is a measurement? Well, at my scale, I'm having light bounce off of me, and atoms and molecules and the gas bounce off of me. My chair is interacting with me. I am interacting both now and throughout my history with a whole bunch of objects. And so a fairly orthodox view is to say that combination of interactions sort of has condensed or collapsed my classical probability into a pretty tight window. Right? So I really am all of that combination of interactions. There are other views which say that there's even extra sort of collapsing agents like gravity, like Penrose's gravity theory. But generally, many people think it is enough to say, if we just look at all of the interactions and the scale of those interactions, how much mass I have compared to the energy scale of those interactions, my uncertainty in position that would be due to quantum mechanics should be so small that it would be unmeasurable. Whereas as we get to smaller and smaller scales, and we look at that balance between the energy scales of the observations, the energy scales of the interactions, the time scales of the measurements, and we find that the uncertainty that one would expect from a quantum theory begins to be at the scale we could observe it.
If we map a wave function, if we consider it physical object, that's also an assumption, it's infinitely large, right?
Yeah, so this paradox, which I actually call Hagerfeld's paradox, right, which is that, basically everything has, this is a little bit of an overstatement, but everything has a chance of being anywhere at any time, right? Hagerfeld was a mathematical physicist who sort of showed this paradox in a very mathematically compelling way in the early 70s. Yeah, this is a challenge to... Okay, so there's two things. So is this a fundamental challenge or is this an observation challenge? If you look at the probability, you're talking about this infinite extent, and you say, oh, let's weight the age of the universe. What's the chance we find Nate over there? You find there's 10 to the minus 27% chance that will ever happen in this universe. So that could just be, it's just very, very unlikely we're going to see this effect.
Well, it depends, right? Because it depends how we interpret the wave function. Whether if we interpret the collapse as the measurement as collapsing the wave function, then the chance is small. But if you prefer the other interpretation, which for some reason many physicists like, which is the many worlds interpretation, in one of them you are at the other side of the universe.
But even so, the likelihood you're in that branch is very, very small.
But that branch still exists.
So in that interpretation, that branch still exists, but so the many worlds hypothesis, very attractive to many people, arguably still hasn't made any prediction that we need it to explain. So I only want to throw that out there. That I have colleagues that I cherish and are still many worlders, love them to bits. No, not throwing shade on them. But for me, the many worlds hypothesis is often held because people are uncomfortable with the randomness, the uncertainty, the non-determinism of quantum mechanics. That is the problem that many people I speak to want to solve. Again, as in quantum mechanics, there's two ways a quantum system can evolve. It can evolve this continuous, smooth evolution, and sort of as you described, right, by that evolution, even if I localize myself right here, almost instantaneously, there's a chance I'm all the way on the other side of the universe, right? Mm-hmm. And again, that's Hagerfeld's paradox, I call it. But what's the... Then there's the other one, which is somebody has to actually measure me over there. And so in orthodox quantum mechanics, the way we mathematically describe those two, the unitary time evolution, this continuous evolution, and the measurement projection, totally mathematically look like different kinds of steps. That seems like a real problem. And many worlds is a way to say, let's get rid of the measurement paradox and just keep this one, which is deterministic and looks more classical than this thing, which is where I believe the true magic of quantum is.
Yeah, but you sacrifice a lot, right? So just to keep the classical view, or maybe even more specifically, locality, right? Yeah. It feels like if you sacrifice locality, that would be sufficient, right? But you don't want to sacrifice, maybe I misunderstand, maybe you don't want to sacrifice locality, and therefore you accept infinite number of decoherent universes. Yes, I know, described as a single decoherent function, but for me, mathematically, I cannot comprehend it as, it's first of all, for me, violation of Occam razor, right? Why do you create so many beings? Are they even beings? If they are they sharing space? What happens to energy? It's crazy.
Where are the branches taking place?
Exactly, they're the same space, how they are taking the same space, and why they are not interacting at all, and yet share energy. How is that possible?
The energy doesn't bother me because we can have, whenever we have a superposition of states, they don't have to, none of those energies are manifest until someone actually measures the energy. And it works out that the energy balance, it'll work out.
So we wouldn't detect it. If many worlds interpretation is true, then the conservation of energy still holds, and we will never detect any leak of energy into the other world, right?
So yes, I will say that is a true statement. Now again, making true statements about the many worlds theory, there are probably a whole host of different possibilities out there, some of whom are more physical, some of whom are more theoretical, or some of whom are even more philosophical. But yes, in principle, the Everett many worlds, energy still is conserved. It can be localized in different places. Any apparent non-conservation of energy is just because you have measured the wrong patch, right? You haven't measured all the patches correctly, but no leaking into some other indeterminate state.
Yeah, for me as non-physicist, it feels like a fashion. It feels like somebody read science fiction books and wanted to keep the classical view of deterministic Leibniz was the Leibnizian world, right? Yeah. And because of that, it biases the potential interpretations, because as you say, that the two popular interpretation, one of them being the Copenhagen interpretations, the measurement collapses the wave function, right?
Right, yeah, the unitary followed by collapse.
And the other one is the many worlds. But there are other interpretations which seem much more logical. If they, it always feels like if they came in a different order. If
Yeah.
Bohr came up with a Penrose interpretation of objective reduction, that would be the popular one. It feels almost like, historical reasons we accept this. What do you think? Like, why, for example, what is the Penrose objective reduction idea, and why is it not popular?
So there are so I would categorize the Penrose objective reduction along with, there's several other versions of this where gravity or some other interaction is literally a physical dynamical mechanism that also works through a continuous deterministic evolution but causes the collapse. And so you said something that made me laugh a little bit, because if it came in a different order, it would make more sense. I guess I am one of these people who don't believe the universe owes us to make sense, right? And so while I am, some people who have my opinion don't want to talk about interpretation then, I'm happy to talk about interpretation, but I do want to acknowledge that a possible consistent interpretation is that it's uninterpretable, right? Well, that has to be in the realm of possibilities, because there's nothing that could, at this point, most of these interpretations are consistent with our observations. And so...
Are uninterpretable as in epistemologically impossible to understand ever, or at the current state of knowledge?
So I'm being a little bit woo-woo, but I would say we can't, it is not a scientific requirement to be understandable.
Okay.
In my definition of science, right? And I don't want to get too hardcore with Popper and reproducibility and all this kind of stuff, but science doesn't owe me an explanation. If I have a method that allows me to predict, retrodict, and describe with an accuracy that I cannot falsify with measurements, that is something that I have to respect. Now, I agree. I want my science to be interpretable. I want to explain things with science. I just don't see that and I may be putting a boundary around what I call science, but I don't see that within the boundary of what I call science doesn't owe me, as some finite human on some random planet, an explanation for itself.
Well, it's a lot to expect that a small system within a system comprehends the whole system.
Yeah, right.
That's true. And I understand that this is a little bit like the Feynman view of shut up and calculate, which was actually a quote from someone else, but he followed it. For me, it's not satisfying. I care less about the practical application. The fact that everything we have here, including this recording system, depends on quantum mechanics, and more about trying to understand it. And I don't necessarily mean it has to be intuitive understanding. Like general relativity is non-intuitive. Like the idea that the time depends on position is completely counterintuitive, but you can comprehend it once you get it, once you analyze, when you see the math, especially the beauty of the tensor math, you will understand it. But that's different than saying that something is completely uninterpretable, and that's very unsatisfying. So I would rather lean toward explanations that have a chance of proving interpretable, and it can be done simply by having them verifiable by experiment.
So I do think this is a good point, and you say something interesting there, right? So it is, especially at first, unintuitive to think about curved space-time and to try to think about higher dimensions and non-Euclidean geometry. But by thinking about the math, one then can access intuition and visualization and other forms of things that help us understand. And then even sometimes when you get intuition about something, you can make that intuitive leap and explain it. So I do think this is one thing about quantum mechanics is I don't think enough people have tried to say, because for example, why I'm not uncomfortable is the mathematical structure is interpretable in that way, right? We can get intuition about this mathematical structure. And in some sense, it's mostly linear algebra, which is just sort of matrices and vectors. Yeah, we don't necessarily all learn that in high school, but it is the language of computers and computation. And so I think that I do, when I replay the tape in my head, saying that I don't expect quantum mechanics to be interpretable, I think I'm trying to go a little bit further in that I'm trying to make some sort of comment about the scientific method that is not something in the scientific method. That is an aesthetic that we can bring to it, and I also cherish that. And probably reality is a hybrid between these things, where we can get intuition from this mathematical structure.
Yeah, so that's interesting. So you're saying reality is part of it. So do you mean that the mathematical structure describing reality, like for example the wave function or quantum field theory, are exact or approximate descriptions of reality?
So I think they are always there is the formalism, and then there are models. So meaning the formalism, the rules of quantum mechanics, or if we start allowing our number of particles to change, quantum field theory. And then there are the models of specific systems. Every model is an approximation. And the question is quantum mechanics / quantum field theory, is that an approximation? That is a good question, and we should continue to ask that question vigorously. So far, we haven't found a system where they haven't provided exactly the result we expect.
How exactly?
So the most famous example is the magnetic moment of the electron, and that's a part per billion. So a part per billion accuracy between like a really complicated quantum field theory calculation and a high precision measurement in an ultra-cold laboratory.
You know, I heard it many times that quantum physics is even superior over general relativity, if you can compare apples with oranges in terms of the precision. But I always wondered, but this is a unit choice. If the unit was one of the over billion, that our precision would be very low.
No,
right?
We have unitless quantities, right? Like one of the great things, the fine structure constant, for example, in quantum field theory, which characterizes how strong, it is unitless. It is a pure number, 137 point something. So
that's why you can claim that this is precise.
That's why I'm claiming this is precise, because it is. There are unitless numbers that characterize the scale of interactions, and that's right.
And by unitless, you mean that you have a axiomat, like a Planck scale axiomatic unit, or you mean that the unit is a ratio between the numbers?
It is a ratio between quantities that have units, and so even if you convert millimeters to angstroms,
units disappear.
Yeah, the units disappear. So it is a pure number, right? So quantum field theory can predict pure numbers that then we can measure. All theories can predict pure numbers. Ratios of things with the same units become numbers. And so that can take away that unit dependence of it.
Also, in this sense, this is closer to reality than, for example, general relativity, because in general relativity, some things break, right? Getting into the singularity, we have no idea because we get infinities. Is there an equivalent breaking in quantum physics?
Oh, yeah, there is. Yeah, there absolutely is. I mean, so quantum electrodynamics is specifically the form of quantum field theory that is, and it's the one that was pioneered by Tomanonga and Schwinger and Feynman. So it really is, in some sense, the most precise theory that we've ever had. Wolfram was trying to figure out how to automate quantum electrodynamics when he invented Mathematica, right? Like, so it is, in some sense, the crown jewel of calculating precise physical observables, especially in particle systems. So some people, including Dirac, and even a young Nate Harshman, was very dissatisfied because you have to do this thing called renormalization where infinities come out, you subtract infinities, but then sometimes there's different kinds of infinities that show up, and it always felt like that a real theory wouldn't act. This is how I used to think. Wouldn't have these these infinities, right? Every intermediate step. I now think of it more like when I do intermediate steps, even in algebra, sometimes I'll have a complex number as an intermediate step, but when I get to my answer, it's real. So I no longer see that as a flaw of the theory, but yes, there are certain questions that if you ask in quantum mechanics or quantum field theory, those questions break the theory.
Yeah, but again, my understanding is limited, but I think this is not equivalent breaking. So I can imagine a theory which describes more than reality. Like, let's say quantum mechanics math describes more than just the reality, and therefore sometimes you're getting out of it, like you go out of the real numbers to complex numbers, but then come back, right? That is not breaking the theory. I mean, an example which would break the theory. Like we know, well, as much as we know about the inside of a black hole, we know that it breaks there, right? The general relativity breaks there. Do we have an example of something like the photoelectric effect in early 1900s, which breaks the current physics in quantum physics?
So no, that would be my claim. Is that I don't know of anything. Or if I do, it's the same place where general relativity breaks, right? Where we don't have a theory of gravity in quantum mechanics because we don't have a theory of quantum geometry yet that satisfies the things we expect out of a scientific theory. Even though attempts like loop quantum gravity and string theory have led to beautiful math, we don't have anything that yet has emerged or has completed as a physical theory. So I basically think it's the same thing. We do not know how to make a consistent theory of quantum geometry that allows us to make calculations that we can compare to reality in any way.
Do we have something, some quantum theory about what happens inside a black hole?
So there are quantum theories. That is absolutely something that I don't. Yes, there absolutely are theories, and people who do string theory and loop quantum gravity and certain various other kinds of foamy ideas would have opinions. I don't have an opinion on that, and of course, it's partially because I was raised in the 1990s when particle physics was going through was beginning what I would say its long crisis, where it was no longer to test the theory without another $1 billion or $10 billion experiment, right? And so that was sort of like a phase change in particle physics, where it really turned out that the brakes on probing nature this way were thrown on by financial realities and by physical realities. A large desert where nothing seemed to be going to happen unless we made it huge new colliders.
You mean you are referring to a Large Hadron Collider and the cost of it and the promise of finding, I think, supersymmetry, right?
Yeah, that's right.
And the fact that we didn't, and so kind of we found a Higgs boson.
Yep.
That's it. For $9 billion, that's kind of expensive.
Yep.
We knew it exists. We now know it
That's
has.
right. So
there.
That's when I made a transition to saying, you know what, there are foundational issues that are not the same as going to the smallest energy and length scales. Right? Some people thought that the most fundamental science was always going to be by going to smaller and smaller scales, like the surface of the black hole, or like these other kinds of sort of exotic features. Whereas I think the excitement of the last 30 years in quantum has actually been in that we can have like almost macroscopic quantum states, right? Starting with Bose-Einstein condensates and now topological insulators and other kinds of novel kinds of material where we can see quantum properties at a macroscopic scale.
Let's go back a little bit because it's related to the interpretation of what you mean by that, like having a quantum effect on a larger scale than an atom or a particle. So what I mean by that is that there is such inconsistency. So there is no inconsistency mathematically with quantum physics, but in interpretation, for me, it is when there is a paradox, when you can point to a paradox. For me, this is an inconsistency. That's like in general relativity, you can point to the paradox of singularity. In quantum physics, in almost all interpretations, you can point to the paradox, and one of them is the famous Schrödinger cat. So the origin, and maybe you can tell the audience probably knows that, but can you tell us what is the Schrödinger cat? And I have a version of it which I wanted to ask you about.
Sure. Well, a Schrödinger cat is one of these animals that's part of a menagerie of science thought experiments. I always say it goes back at least to Laplace's demon, who was the nimble-fingered spirit that if it knew every particle position and momentum, and it could calculate the future with ultimate precision, right? That was Laplace's demon, and then Maxwell's demon, Boltzmann's brain, all of these creatures, right? So first off, I just like to put them in this this menagerie of scary physics creatures. So Schrödinger's cat, we have some sort of maybe it's a decaying nuclear decaying atom. or maybe it's some other unstable quantum system where we can detect when it decays, but that detection in principle is, following the rules of quantum mechanics, a probabilistic event. And it depends, at least in the standard sort of Copenhagen shut up and calculate way of doing things, in that until it is measured, there is no answer to the question, has this atomic nucleus decayed or not? Now what we do is we couple the state of this nucleus through a Geiger counter or some other detector to the classic is the cyanide tablet or the cyanide capsule that gets broken and kills the cat. I think these days when we teach it, we do say it just puts the cat to sleep. These days, that's the softer version of this. But yeah, so then the idea is we have this box that has a cat in it, and according to sort of the orthodox interpretation, until Schrödinger or Schrödinger's friend or the cat's mother, whatever, looks at the box, nothing. We don't know whether the cat is dead or alive. It is in a superposition. Now, how would we detect that superposition to know that's true? Well, then what we'd need to do is have an entire array of Schrödinger cats and do interference experiments with them. So that's the experiment that nobody's ever tried to do, well, with cats. They do it with electrons, and it seems this kind of thing, did the electron pass through slit A or slit B? It really looks like it did pass through both of these possible slits until we measured it.
Yeah, but the electron is not conscious. At least most people think that it's not.
That's right.
I know some crazy people who do think that fields are conscious. The cat is conscious, and not only conscious. Cat might be, according to my wife, who prefers cats over dogs. Until recently, you met our Layla, our dog. The cat could potentially perform the measurement itself. So if the cat is in a box and performs the measurement, the result of this measurement in Copenhagen interpretation is that the cat either dies or survives. So it's a half-suicidal cat. Now, for the person observing from outside and treating this system as an isolated system, that cat is still in superposition. And that, for me, breaks the logic of this interpretation. How can something be in the same time in superposition and in collapse state? I accept superposition. I can imagine two cats in two versions. That's possible. I cannot accept that the cat is at the same time alive and dead for external observer and not from the cat's perspective.
Yeah. Well, okay. So, and again, as you pointed out, many worlds is one way people have tried to resolve this, because then the cat's just following its path and these things are consistent correlations. Or I would say a more orthodox explanation would be, well, the real problem is these are macroscopic systems. They are hot, wet, and interacting with their environment. And so the measurement, this idealization of a measurement process actually is taking place a lot faster. It doesn't require consciousness for it to be a measurement. It only takes a scale of interaction to where a large enough chunk of reality that's all connected by interactions begins to act consistently. I would associate, I don't know whether Carlo Rovelli, I don't know if you've read any Carlo. Yeah, I don't know if he would accept it. That's how I would sort of match his theory of sort of relativism, of this kind of quantum relativism with sort of the decoherence theory, which is pretty standard too. So I think that's one sort of way a person would walk out of this. Then there's finally, of course, the shut up and calculate people who will just say, yeah, show me an observable consequence. Show me how I would measure that this paradox is a paradox that I could observe. And if I can't observe it, then I'm not really certain what we're talking about.
That's an unsatisfying excuse. Because we can imagine.
I gave you two other answers.
Yes, that's true. But we I mean the last one, the idea that we should not try to understand it. But you said that there is reasons for it. But okay, so my counter argument would be the following. So cat is big. Okay, it's hard to make a quantum cat. How about making a really, really tiny nano detector?
Yeah.
Which is made of few atoms and do exactly the same.
So then you have a superposition of something that's made a detection or has it. Like you just have a chain of superpositions.
Well, okay, but that from the perspective of that detector, because we are eliminating the consciousness.
From the perspective of that detector, so maybe we would say if the detector, so I am making a hypothesis here, or I'm making a claim, something where we will be able to see something that is conscious every conscious thing I can imagine already has to be at a scale to where decoherence is relevant. Now, I know I'm going to sound like Penrose and microtubules. Like, I've got to be careful around here. Somebody's going to come out and attack me for microtubule support, but yeah.
We will get there because I love the microtubules, because that's the only interpretation which actually have, as far as I know, strong experimental evidence recently. I don't know if you read the papers.
I have not seen any recent evidence.
A year ago there was a paper. Yeah, but still, okay, so because that introduces the consciousness, right? So is there a role of consciousness in collapsing a function or not? If we say that measurement has to be performed by an object, like a detector doesn't need to be conscious, it collapses the function anyways or not. So how can we from another perspective see that measurement are not yet performed in superposition with one when it is performed?
So again, this is a challenging topic, and I would say that that heterodoxy is still orthodox, all right? So I really would say that this is something where you're absolutely right for pushing on this issue, because this is where interpretational rubber hits the road, right? So I take this. There's a couple different things I want to keep trying to say, which is we can still think about scales, and so what's detecting that the detector has detected, and most sort of theories of interaction, if we have this cascade where the thing that detects the detector is a little bit bigger than the detector, and then the thing that detects that, like maybe we're talking about a camera, but then there's the wire, but then there's electronics. We can have a chain here, and at the smallest scale, we can think of just a screen with two slits as a detector. And so when we get down to that scale, we have perfect evidence that there is a superposition. I'm not going to grant a screen with two slits as conscious, and so you're right. But as we go along this scale, screens after screens after screens after screens, where are we going to call that thing conscious? Yeah.
But even what you just said, this is very interesting. So basically, the idea is that the chain of detecting what detector did at some point has to become macro, and that will cause the collapse.
Yeah,
that's very cool, but that feels to me almost like a support for these theories which say that the scale is the essential element, and like one of them, let's go there, is the Penrose objective reduction under gravity. For me, this theory is the most convincing as I said, non-physicist, because we would be able to do, at least I can imagine, we would be able to design experiments where we verify it or not. Like one idea I came up with, you can kill it. Like let me be an experimental physicist. So we know the equivalence principle, I think it's called, right, between the acceleration and gravity. So we can like kind of counter the gravity but by acceleration, let's say, if it's true.
Locally,
yeah. So let's put an experiment into a rocket. We accelerate it in such a direction that it counters the gravity, or we drop it from space. That's good enough. Free fall, right? Free fall, or in a satellite or something which would basically make sure that there is no gravity effect on that object. And we see if we have, let's say, more larger objects collapse later. Maybe not that late, but they collapse later because there is no gravity influence on them. And then we compare if that rate of collapse or the size of or the number of atoms and particles required would be different in a strong gravitational field.
Yeah, so first off, we do use quantum systems in free fall to test the equivalence principle. This is something that is used. A variety of different experiments have been done like this. More, of course, because we actually have more confidence in our precision of quantum than we do of our gravity, so we can use these quantum systems as very precise measuring devices to look for gravitational effects. And so first off, this is actually technologically feasible. The question I have is, and I have to think about this, is how would we test the time scale of collapse? I don't immediately know the signature measurement that would detect that, but let's even grant that. If we can come up with that, then yes, somebody should do that experiment, and I don't think there'd be any resistance in the physics community if somebody could figure out a way. So I'm guessing that the crack, or the hard part, is finding the right measurement to make where we really feel like we are measuring the time scale of the decoherence.
I also meant so time scale is a very interesting idea. I didn't even think about it. I meant the size of the object. So I meant like 1 atom, 2 atoms, 5 atoms, 20, 300.
And I was presuming that the size of the atom would be correlated to the time scale of the decoherence, simply because the way these theories typically work is the bigger it is, the stronger the gravitational interaction, so the faster the collapse.
I forgot that the object itself has mass too. So
yeah. So
right.
Yeah. So
the more atoms, the more mass.
Yeah, and I would guess that that's the more important mass. Yeah, because we are probably looking for effects at a super local scale.
So that would be a way to verify, and that seems like a very classical approach to, Penrose is really a general relativity more guy than.
Although I actually use the Penrose triangle in my research, so.
I made the Penrose triangle logo of my institute. So if you visit us, I love.
If you have 3 indistinguishable particles on a ring, quantum indistinguishable particles like bosons or fermions, the configuration space is a Penrose triangle.
Amazing.
Yeah. So,
although I don't understand what it would mean, because the Penrose triangle is very strangely 3-dimensional to 2 dimensions, right? Into 4, so sure, yeah. Well, cool. That's very cool. What about other interpretations? Like I heard about a pilot wave interpretation, which seemed to me like breaking the Bell's inequality, but then I realized that I didn't know enough about Bell's inequality. Maybe you can explain it to me better. But one thing I wanted to say is that the Bell's inequality is violated for non-local interpretations. If we abandon locality, then we can have a pilot wave or hidden variable theory as interpretation.
Yes, and and certainly, so there's some sort of a web of locality and causality tied together, and again, there's sort of several different concepts in that in that sort of space. That is orthodox, and the evidence that would take to break that, like if the only place we saw locality broken was was in violations of Bell's inequalities, right? That wouldn't be enough. We would need to see other violations of locality in order to have a compelling reason, since we have a completely local theory that explains it, right? In other words, we would need to have very compelling other evidence that we should have such a wild upending of all physical theories for an interpretive motivation.
So I see. So locality is so essential that people think it's absolutely, you would need a tremendous evidence.
You would need extraordinary evidence. Now, for example, non-locality can be an evidence of an effective theory. So people study non-local things, but they usually say this is not the fundamental theory, this is an effective theory. For example, we know that electromagnetic waves travel at the speed of light, but nonetheless, if I'm solving the hydrogen atom, as in my first case, I just treat the electric field as though it's a classical field, and then I do quantum particles in that. That's actually making a non-local approximation, a non-local assumption. But we do think, and there was a lot of work to try to make sure that to prove that this was essential, right? That axiomatically, I used to want to be an axiomatic quantum field theorist, right? I used to want to literally be able to say, like, these 6 mathematical statements, these 9 definitions, and I can prove everything. And this was a big effort in the 60s and the 70s. It sort of petered out in the 80s, in my opinion, to try to axiomatize. And people decided in the end you had to have locality as an axiom because it's super powerful mathematically. Yeah. Once you put that axiom in, many things are determined. And so even though I'm still skeptical of axiomatic quantum field theory as a science-generating structure, it is still essential to all of our foundational theories.
I'm so surprised with what you said because I assumed that locality is dead in physics. So this will be my big confusion. How can there be locality when we have entanglement and quantum tunneling? How is it not contradictory?
Yeah, okay. I mean, no, this is a fair, and so it really does come down to what do we mean by these terms. I mean, so first let me give you, sometimes you'll hear explanations of entanglement that are actually like what I'm saying, but they're a little disguised. Say I have a bag, and I put in a blue ball, or I have 2 bags, and I have a blue ball and a red ball, and I don't show you which one, but I put a blue in one and a red in the other, and then I give you one of the bags. You go all the way across the universe. When you open your bag, as long as you trust me, if you see a red one, you know I have a blue one. That's non-local in some sense, right? I've signaled you. I kept the blue one. You have the red one.
But you haven't because you made a decision before we
absolutely
traveled with the bag below the speed of light.
So that's a correlation that's based on a decision I made. So what we really need to show to see the magic of Bell's inequalities is the interference between measurements, right? We really need to make a quantum measurement and see that I have the statistics of my observations are matched to your observations. But to do those matchings, we do have to communicate with each other. So that is I'm just trying to say that is something where we can't do any sort of signaling with entanglement because to see the entanglement, we have to already have communicated.
Yes, but that I understand there is the non-signaling theorem or theory which kind of presumes that you can't pass information between 2 objects. But as far as I understand, it doesn't presume that you cannot pass information, that things can happen at a distance as long as information is not passed. So performing a measurement on entangled particle can at this moment collapse the particle in the other entangled particle in a far away place, as long as there is no way for that other observer in looking at the other particle to get any non-random information from it.
Yeah, that's fine. Yeah, absolutely. So but again,
and that requires non-locality. This is non-locality.
So, but again, what I'm claiming is that non-locality is the same as the red-blue. Right? You look at red, you see red. I have blue. But that doesn't mean mine collapsed. It just means that, there was a correlation and you have revealed it.
Well, but if we assume that the wave function is real, then first of all, let's say in the many words interpretation, then we have 2 different outcomes of this measurement at the moment of measurement, not at the moment when we entangle the particles, right? So,
but the state is determined. Like that whole evolution from when we create the pair and and until the measurement, that is a continuous unitary evolution, we presume, whether we're doing many worlds or canonical interpretations.
So you don't believe that there is at the moment the spin of this particle is decided at the moment of measurement. It is, or this is an interpretation which we simply don't know and we'll accept it.
So okay, so I mean, so first off, this is a real issue, and you will get different opinions about this. So we're about to start getting into: do I think the wave function is psi-ontic or psi-epistemic? Right? Mm-hmm. Do I think the wave function describes reality, or does it describe possible measurements, possible information about reality? And so my intuition from the math is that I've got this state, and this state is represented to me as vector in a Hilbert space, but it's a pretty well-defined object and mathematically not that complicated. In terms of it, I can think of it as just an array of complex numbers. And so then measurement is these operations I do to this vector. But the vector has information in it, and these different observations just reveal the information in it.
So you're operating on a Platonic reality of the math, not on the reality. There is no direct mapping, even if unknown, between the space-time, the space, or whatever, the reality under the space.
I'm going to dodge a little bit. I'm going to dodge, but I think it's a fair dodge,
okay?
Okay? I make a map of the Earth, I do a simple projection, the North Pole ends up a huge long line at the top of my map because I projected a sphere onto a rectangle. Am I saying that the North Pole is a line instead of a point? No, I'm not saying that. I'm just saying this is a problem with this particular chart of reality. So I'm trying to dodge into say that quantum mechanics is a really good map for a certain part of reality. I still find that my map blows up a little bit sometimes at these particular incidents where I have to try to make a claim about reality. It doesn't a lot of time, right? When I'm talking about a hydrogen atom and I talk about quantum mechanics, I have no trouble.
Because you're close to the equator of the map.
Yeah, I'm close to the equator of the map, right? And in some sense, right, the hydrogen atom is one of the simplest quantum systems to describe, and it's ubiquitous in the universe. Which I always think is sort of funny, right? It's the simplest thing to describe and the simplest thing to observe and have around us. Sometimes I feel mystical about that, if you want to get me woo-woo. So I agree that entanglement is a place where a certain way of thinking about what is reality gets really close to where the map gets just so distorted. But when I look at this other map, which is provided by the math, it's a really clear picture, right? So I, to me, what that tells me more about, though, is trying to map it into the words that we use, and this is very Niels Bohr, right? Is that really it's the incompatibility of the physics with the classical words and structures that we want to use to try to describe it.
Yeah, the map analogy, I've never heard it. It's brilliant, but it also kind of directs me to the interpretation of quantum physics when the information about the system is the most important and it's relative. Maybe kind of ravioli.
Yeah. Carlo Rovelli.
Ravioli.
Or
sorry, Carlo.
Oh gosh, can I get his name right now? Quantum Bayesianism.
Exactly, that was
right?
the name. Yes.
Yeah. So,
yeah.
I've heard very good talks on quantum Bayesianism, and whenever I walk out of a talk on quantum Bayesianism, I am momentarily converted, like it's a revival, right? And this is one of my problems as a scientist. Like every time I hear an interpretation of it the first time, I feel the spirit move through me. What is it? Quantum modalism. There's a bunch of really great little ones. I shouldn't say little ones. I don't mean to be condescending, but there's lots of different ones. And certainly so I started out in particle physics in the 90s, and then by the late 90s, of course, Grover's algorithm and quantum computing started exploding. Shor's algorithm, thank you. Shor's algorithm started exploding. There suddenly ended up being a bunch of interest in what had been, like weird little toy models that nobody had really thought very much about, right? And some of the leading people in quantum information theory in the late 90s had actually been like at little liberal arts colleges, because those were the only places where you could still get tenure and still have a good career and get to think about foundations of quantum mechanics. But then in the 90s, it exploded. I always had a little bit of a foundational kind of edge to me. So by the 2000s, I'd switched completely over to quantum information theory. And that was my personal high water in psi-epistemic, in believing that all quantum mechanics told us was information. And it's a little bit of a different twist than just the shut up and calculate, because it isn't saying that it's just shut up and calculate, but it is saying I'm going to be agnostic about ontological claims about what's really there, and instead think about the information as though the it comes from the bit, to quote Wheeler, right? It from bit. And so I've been through a phase in my life, about a decade, where I was a hardcore it from bit, that matter was built on an information substrate. I have now come back a little bit as I hit middle age, rolled over to sort of a more middle-of-the-road view of this sort of maps. That sometimes when I'm doing quantum mechanics, it just tells me very clearly what's happening, and I can talk about electrons and protons forming hydrogen atoms and emitting photons and have no queasiness at all about ontology, right? And other times when I try to get to, and even still when I try to actually think like, okay, I'm making these measurements at these distant locations, and I try to get into the ontological perspective there, then I just switch over to the math.
Mm-hmm. So you basically are suggesting that you're not really the shadow and calculate, but more information is the essence here, and the reality is like a reflection of what information is contained in.
That's right. And what's nice about that is that some of the strengths of decoherence and thinking about sort of the coarse graining of the universe into patches that are interacting strongly enough to where the quantum decoheres into the classical, that also can be formulated in this sort of information perspective, and that these sort of becomes networks of information collectives, and there can be a really nice sort of picture there that, again, you see I'm already leaning into an almost an ontological picture of information, but there is, but I find that can be satisfying.
Do you think...
but science doesn't have to satisfy.
Yeah. Do you think that there is a relationship between what you're saying and Wolfram approach? Are you aware of his hypergraph the new theory of everything, where he uses a hypergraph and well, maybe you know better how to explain it than I do. So
so I thought you were, and so I don't know it well, but I was thinking about automata, right? Quantum automata, and trying to think about this informational perspective as that, can we imagine the entire universe as built out of information dynamical systems that follow the rules, or I can't even remember if they follow the rules or create the rules of quantum mechanics through their computational origin.
Yes, it's very much this, but very recently, and I know he's being ignored, so I'm not surprised if you haven't heard about it, because he's really not accepted in physics community because he's a mathematician and computer scientist. But as a computer scientist, I know a little bit about his work. So this idea grew out of this emergent system from automata and simple rules, but he refined it into a hypergraph theory. So basically there's like a hierarchical structures of hypergraphs, which each have specific rules of how computation is done from one place to another, and that graph is supposed to represent every possible physical quantity, force, interaction. Now, this is very vague, and we will need to go deeply into this, but what is fascinating for me as a computer scientist about it is that what he finds the most important is that he believes that the universe is essentially computable, and any observer who is looking locally at the universe is a computational machine, as I understand, like almost like a universal Turing machine, and therefore has a very limited view on it. If a person is unbounded computationally, then all the problems of interpretation of quantum physics disappear, because, for example, it doesn't require locality, right? Like if you're computationally unbounded, you can go anywhere in this graph and compute anything you want, and then you have a knowledge of that graph. That doesn't mean that this entity exists. It means that if you presume such entity exists, that entity would resolve the unbounded computationally entity would resolve the problem.
So I don't know this theory. There's parts of it that are immediately satisfying to me in the sense that, I mean, and so I imagine in this theory then, since we are all bounded, then that is the paradoxes and uncertainty of quantum mechanics comes from our particular local boundedness, our finiteness. Very satisfying. I have to say that any theory that claims, again, because of my sort of almost any but the simplest topological spaces can't be covered by a single map. Why would I think that the universe is less complicated than a sphere? right? So I have to admit, I always walk into any claim of one theory to rule them all. Obviously, this was a long fantasy, I will call it a fantasy, of science, that there would be one theory that explains everything. Whenever I hear a physicist claim that they have made one theory to rule everything, I've got to also be like, the physicists who actually did do the theories that changed everything usually didn't make their claims that way. That's not how Einstein wrote about his theories, right? He didn't say, I'm changing everything. He wrote a bunch of random papers in 1905 that just changed everything. And then as he was working on general relativity, he knew he was working on something important, but he made mistakes and went back and forth, and it was still a really humble process. So I gotta say, love Wolfram. I use Mathematica every day, and he made that. I use it every single day. It's a weird piece of software, but I love it. And I teach it, and I really think it's an important cultural contribution. It's changed how I think. I think cellular automata. I think this kind of stuff. But I gotta say, when I hear it sounds a little megalomaniacal when somebody postulates there is an unbounded computer for whom everything is solvable. I can't see that old Wolfram isn't up there in his Wolfram throne, imagining that he's that one, right? If he says he's got the theory of everything.
I think he means more.
Sorry.
Yeah, I see. Well, let's go to this theory of everything, because I think some people claim less than what you are saying when they say that they have a theory of everything. So what I mean, they usually, I imagine, maybe I'm wrong because you would know better, I imagine that they mean only the unification of gravity with other forces, not that there will be no paradoxes and unsolved problems, because if they did claim it, then I would consider it very suspicious for the reasons of Gödel theorem.
Yeah.
And
exactly.
Simply because any mathematical solution complex enough to include arithmetic is going to have Gödel sentences in it, which are sentences which cannot be proven or disproven in that system. So how can anybody claim to have a theory of everything that works for everything? I can imagine somebody having a theory of everything that works for almost everything, let's say,
chart.
Except for singularity, right? In a black hole, but not everything. So that's, I don't think he's claiming that. I think he's claiming kind of the opposite. And again, we will need to ask him, but I think he's claiming that you cannot write, it's irreducible. So you cannot write a formula. Physicists want to write a formula. They want to write like a second law of thermodynamics, or they want to write like a wave function, right? They want to write it in a closed form. And he says that most of the word is indescribable this way because the computations cannot be simplified. They have to be performed. That's his claim, and I find it very interesting.
Oh, but I would say most physicists agree with that. Mm-hmm. I mean, very few dynamical systems. So, for example, most dynamical systems are not integrable. Integrable is where you can, at least in principle, write them in a closed form. We now know, at least since the 60s, that most dynamical systems, right, that was the fantasy that everybody would write these formulas. But since the 60s, most physicists, I would hope, know that we can't write closed form expressions for basically more than two particles.
But they are still computable.
But they are, so then it depends on the dynamical system, on the different scales of computability, right? Mm-hmm. I mean, are they chaotic in that, sure, they're computable, but any small variation in the starting point of the computation leads to dramatic differences. Mm-hmm. Each step is computable, but the steps become wildly inaccurate. And then there can be systems which are also on top of that complex, where the actual rules themselves are hard to discern to the point where we don't, I mean, so computability is hard even to, maybe for me to formulate in that thing if we don't actually know, the complexity is such that we don't know, there's a mixing of scales to where we don't know how to make an effective theory to do a computation with.
Mm-hmm. But do you mean that there exist physical processes, objects, or systems which are non-computable? Or we just don't know, we don't have a measurement of an initial state? Right?
So about 10 years ago, the ironically named Tony Cubitt was the first person I know, I think it was Cubitt, but anyway, he had co-authors, wrote the first paper I know about claiming there really was a physical system that was incomputable, and it was equivalent to the axiom of choice as to whether the ground state of this condensed matter system had what was called a gapped ground state or a not gapped ground state. So there are a few physical systems where people have claimed, based on an axiomatic approach, that they are undecidable in a finite universe.
Very interesting, because in complexity theory in computer science, we learn in the first year of the first class that most problems are incomputable.
Yeah.
The vast majority problems, a continuum of problems compared to Aleph zero problems. So larger infinity of problems is non-computable. But it doesn't necessarily map to the physical reality. It's mathematical reality. And only in the discrete math also, like it's not, you don't need to go to the continuum. You can show it in discrete 0-1 operations, right? And I never knew that there can be actual physical objects.
Yeah,
Is it proven, or do you think it's a one point like that?
So this is a thing where I will say I feel confident that this is true. However, I am not an expert in this. Like, in other words, I am expressing a confidence based on I read these papers, felt pretty confident that the math was right, and that this seemed plausible to me, that their proof, again, some people criticized it because it really ended up being, well, it depended on infinity, right? It depended on which kind of infinity, you were choosing, whether, the power set of Aleph 0 was equal to Aleph 1 or not. Right, and so some people said, well, if we're in a finite universe, its computability is definitely decidable, because, like, if you have it's a finite system, so you're going to eventually cycle through your Turing machine, so to speak, right? However, I am now speaking about my intuition. What I study is where algebra breaks down in quantum systems. So I study symmetry in quantum systems. And when you have enough symmetry in a quantum system, then you can reduce this mathematical model to algebra. Algebra is beautiful. Fundamental theorem of algebra says every algebraic equation has all the solutions you want, right? Or all the solutions you could expect. If you don't have enough symmetry, you have to start doing analysis. Calculus, the first step, right? You have to start worrying about whether there are solutions to these things exist. And you can certainly prove sometimes that there are no closed form analytic solutions to a whole bunch of different kinds of problems. So I really study sort of the ragged edge where symmetry breaks down and you have to use a totally different kind of computation. Based on my experience there, I believe that that there are uncomputable things. I mean, for example, I even know, right, once you even get to taking the eigenvalues of a big matrix, a pretty simple, like, quadratic problem, computational problem, a small variation in the parameter can lead to wildly different outcomes. It can lead to chaos, even in a really, like, a 6x6 matrix. So it is conceivable to me that there are incomputable physical reality, and this is relevant. This is something I've believed ever since I read Roger Penrose's Emperor's New Mind, just as I was when I was in college, right? So this is the influence of Penrose on me from all the way back then. That, and of course Gödel, Bach, right? Between those two texts, I have this non-scientific aesthetic faith that incomputability is important to understanding the universe.
But you don't agree with Penrose, I suppose, that has anything to do with consciousness, or you do?
So, I mean, I think that you promised me that there were recent measurements. I would love to. I am compelled enough by the idea that recent measurements are interesting to me. I would say my claim would be that the orthodox view was that in this regard, Penrose followed the path of Eugene Wigner, another great theoretical physicist and expert in symmetry, who also went down the path of trying to figure out the role of quantum mechanics in consciousness. I mean, this is a path that eminent physicists have gone down as well as the pedestrian. So it is an important and interesting question. The orthodox is that it is misguided. The orthodox is, and I have not looked deep enough to know other than the criticisms are very shallow at the very least, right? Like, what does Penrose know about biology? On one sense, that's a really shallow criticism. On the other hand, it can be a devastating criticism.
That's right, but he's working with Hameroff, and Hameroff is a professor of anesthesiology, and it was not Penrose's idea. So Penrose only introduced an intuition, right, in this book, that since we supposedly, or mathematicians, he limits it to mathematicians, understand the Gödel theorem or undecidability in Turing, the same kind of thing, let's say, for non-orthodox view, we can understand which side is true and which side is not true. We feel it intuitively, and the computer will never know it. Then there has to be some kind of process which is non-computational, which happens in a brain, and the only thing he could think of would be a quantum level process which introduces undecidability. Now, that's the only thing he claimed. He had no idea about biology. Then Hameroff comes in and says, what I observed, I don't know if you know this details, I'm just referring
I don't, please.
It's really interesting. So what I'm reading your book, and what I observed in my clinical practice is that there's a very strange phenomenon that if I give anesthetics to people, it's not the activity of the neurons that it interacts with. So the gases given in anesthesia, they're noble gases. They shouldn't interact with anything, not that much. They shouldn't be like biologically active. And if they were, there would be consequences like toxicity and so on. But what they seem to do, they seem to stop the vibration of microtubules, which are nanostructures within neurons and actually every cell in the body. And they stopped that vibrations. And that was what he observed. He said, well, so maybe this is something, it says very, very small structures, like they look like pipes, tubes, right? And maybe it has something to do with quantum effects. That was, 1990s or maybe early 2000s, I don't remember. But 2 years ago, and unfortunately I don't have this paper in front of me, so I'm trying to remember what was exactly shown. There was an experiment with light emittance under certain circumstances from microtubules, and what was observed that microtubules were almost as small as required. They're basically structured like nano tubes, right? So a few hundred atoms, I think. They seem that the structure, the geometric structure of these microtubules seems to prevent the coherence. Okay. And that's the current state of evidence. I would need to read the paper, but at least you see like a little path. Like there is a theory. The theory is verifiable by experiment. Somebody comes in, says maybe that's the structure. Then 20 years later, you have an experiment which shows there is some quantum activity. That doesn't mean that quantum activity causes consciousness.
Absolutely.
That's far away. But it's better than just saying what other theories of mind.
I mean, so I think this raises an interesting question, right? Because, for example, there's also I saw several talks where so quantum biology, right? Various talks where quantum phenomena are important for if you can't explain the efficiency of photosynthesis without thinking that there's some extra quantum coherence, right? There is a certain kind of polarization detection in bird eyes that they use to navigate that requires quantum effects. So I will say 20 years ago, people were deeply suspicious that you could have quantum effects in warm, wet, living things. Now there is true evidence of that. And besides, I don't know these microtubule recent results, but there is true evidence of that. So that does give some opening, right? What do you want out of a theory? You've got to at least have a mechanism. So at least now we have a mechanism that there could be quantum effects in biological systems. I believe that is established at this point, that in chemical and biological systems there can be require quantum effects. Now sometimes I worry what we're going to find out is that it turns out, oh, wait a second, this is actually ubiquitous, but not important. Do you know what I mean? Like it could be that, right? It turns out, oh yeah, well, I mean, now that we know how to measure it, sure, at that small things we can measure quantum effects, but it still didn't turn out to be relevant to.
Yeah, that's possible, but I'm surprised that it was not kind of intuitively obvious, because it's only theoretical or mathematical distinction between the quantum world and the real world. There is actual continuity. There is no border between them. So there must be maybe invisible, maybe unimportant, maybe small.
Well,
am I going interaction, right?
Yeah. So I hear what you're saying, but of course, one of the things we've actually learned from quantum mechanics is that you can have what's called a first-order phase transition, where literally over some temperature, the behavior is totally different. So that logic where you would have some left over, no, if you get above the critical temperature, you don't have a condensate and you don't see any evidence of it. It's a first-order critical point.
And then you have the opposite example, like the sun, where we have all the energy from the sun thanks to quantum tunneling, which is very visible. Look at it.
Absolutely. Yeah. So and in some sense, almost all light, all light emission and absorption is fundamentally a quantum process that can be, maybe I shouldn't overreach, but could be mapped onto tunneling productively, right? Could be usefully mapped, simplified at least onto a tunneling model.
Yeah, so that's why I'm fascinated with this idea, and not necessarily, because this kind of leads to, I think Penrose was misinterpreted because he sounded unscientific, or almost like a little bit like a mystical there, like there is some process we don't understand. But he's a materialist, an atheist. He always says that he doesn't believe that there is some. He's not a dualist at all. He thinks that the physical process of quantum computing is an essential for consciousness. So why it is dismissed when it's verifiable? It's very strange,
So I think that, So why? So first off, I think some people just do misunderstand. I actually think there is a lot of resistance to. I talk to people every day who still barely believe in either chaos or Gödel's theorem, right? I do think there is, even among, and I would say, even among natural scientists, physical and biological, can be resistance to things that come from math, right? And particularly these kinds of incompleteness and arguments, I think really are hard for some people to swallow. In the same way that, right, I still get multiple emails a month for people who can't swallow the lack of determinism within quantum mechanics, right? These things are new. These are new ideas, and they countervail against Newtonian and Leibnizian ideas, against all sorts of kinds of determinism that we have thought, that we have held sacred as a society, at least a Western society, for a long time, and have built into a kind of rational model of our economics and our legal systems and all of these things, right? So I think there's a natural resistance to this. Literally in our 10-year guidelines in the physics department, I've inserted Gödel's theorem, because I want to say in our 10-year guidelines, there's no chance that we're going to come up with an axiomatic system for tenure, right? That's going to be complete and computable. So
it's very that you are pointing at a very interesting historical sociological issue. I have exactly the opposite problem. I would not like the world to be deterministic. I would find it extremely sad. That has so many consequences, like no free will whatsoever, and so on. Why people want that?
There's a resurgence of deterministic thinking, both of the physical determinism and the social determinism going on right now. So I agree with you. I find space, and this is even, of course, why do I want Penrose to be right? It's because I want to find a materialist place for free will, right? Of course I want to find that. And so I think there's also, me in particular, why do I keep this theory at arm's length? Is because it is seductive in itself. Because of course, if I want something to be true, that's where I've got to turn on my skepticism dial all the way to 10.
That's true. You have to be careful with this bias, but there seems to be a very strong other bias, like this determinist bias, right? This idea that since you learned from childhood the formulas for Newtonian physics, which is completely deterministic, then you cannot swallow the fact that it is actually not deterministic. So there are both sides biases, and it seems that, like, I don't know really how it is, but it seems that most people are on the side of determinism, including Wolfram, who is basically saying it's non-irreducible total determinism.
Yes, I find that I would agree with that. I mean, so there are most physicalists and most people who believe, most people who are educated enough that would say something like, yes, science is real, also end up being determinists. I agree with that, right? And so I always find some of those signs, right? Like saying science is real, to me, that's almost immediately a sign to me of deterministic thinking, just because that's such a, for me, a meaning, and I hate to criticize. I'm so glad that people have political opinions and have ideas and things, but I am also concerned about determinism. I think that it is a strong bias, and I would argue that, again, I'm at American University, A is near the top of the alphabet. I get emails literally every day of somebody proclaiming a theory. I got one just yesterday proclaiming that the sun is antimatter, the core of the earth is antimatter, and your eyes have antimatter in them, right? And so I didn't click on it, right? That was all in the title, right? So I get these emails every single day, and I still claim that most of them are trying to restore more determinism to the physical world.
Interesting. I would rather see the movement to restore in quantum physicists are indeterministic mostly. I don't know. I just feel like the world would be extremely boring if it was completely deterministic, and it's much more interesting being non-deterministic, which allows for.
And I would say what's most interesting is a hybrid between the two of them, right?
Yeah.
Right. I mean, I really where it's most interesting is exactly where they meet, where things are really close to that tipping point between being deterministic and being non-deterministic is probably where the most interesting scientific questions for resolving the paradoxes and the controversies you're trying to describe, the interpretational matters. That's probably where to look.
Mm-hmm. Do you think this is related, but kind of, or maybe orthogonal? Do you think that the world is continuous or discrete at the fundamental level?
I have. So this question again. So I first want to answer as if I had to make measurements to make this determination. I still would say that every measurement we have is that matter is discrete, but space is continuous. I would still say that's probably, and when I say matter, I really just mean matter and energy. I'm counting massless things too. But I still would say that is probably the most orthodox answer. Now, again, there's the cellular automata people, and there are loop quantum gravity. There's a bunch of people who have looked at fundamentally, is space discrete, or even more boldly, are there other discrete structures for which space-time itself as an approximately continuous thing emerges? I think that's more of a Wolfram perspective also. So measurements are fundamentally discrete. Information is fundamentally discrete.
Okay.
And so for me to talk to you, I can only talk to you of discrete things.
Why do you think that space-time or space, if space-time is too hard to determine, is continuous? I always thought about it, since there is a Planck length and below that we see nothing, I almost assume that somewhere below the Planck length, it could be discrete. So this must be related to the math of describing it, right? Like that's the reason that, the general relativity doesn't work on discrete.
Yeah, I mean, one of the things that's true about the Planck length, right, is that's the event horizon size. Like, that's where literally quantum fluctuations create black holes. So that is certainly a place where our theory breaks down, right? Now the question is that also where space and time break down, or is that where our map breaks down? And so I don't know the answer to that question. What I know is that even if we can measure very, very high momentum objects in particle experiments, and by Heisenberg's uncertainty principle, which we have a lot of confidence in, that does correspond to very, very, very small length scales. And we see no graininess on that side. Again, we can, by Heisenberg uncertainty, by measuring high momentum things, we can, in some sense, measure very, very small scales of position. And I don't think we have not seen, yeah, particle experiments then end up being very expensive. To get even close to the length scales we're talking about, right, we still have, what's the smallest scale we've measured? Maybe 10 to the minus 18 meters. I think, what's Planck length? Still
minus 24 or something?
Yeah, I was going to say 30.
30
yeah,
maybe?
So
very small.
So, and let's just say for each order of magnitude, we need another
$1
billion, and not just a billion per. A billion, then 10 billion, then yeah. So, and we may need to make a galaxy-sized detector to get down there.
Yeah, I've heard that ideas. That would be awesome. Well, let's wait for fusion. Energy become free, then everything is free. Then we can build these detectors.
We are waiting. I am waiting for fusion. I've been waiting for fusion for a long time, though.
I think the fusion's coming. You don't feel like it's coming? It's a hype.
So, you probably heard this joke before, but fusion's 20 years in the future.
Yes.
And always has been.
Yes, I know this joke, but that was a good joke until recent breakthroughs, maybe?
Okay, so I am happy that the National Ignition Facility had more energy come out than go in. That is a long way from being able to harvest that energy for a heat engine of any sort. I've heard, especially people are pretty hepped up about, right, using AI and machine learning to do genetic algorithms to make reactor designs and test them faster, and that's really going to come through.
Well, and actually to stabilize the
field
confinement, magnetic confinement, for example, in these types, right? It doesn't seem like, if you can do it fast enough.
Listen, if I had money, I would put it into this. I agree with you in that way, and I would have put a lot of money into it for a long time, and we might have already had it. I'm just always a little cautious because same with the quantum technology revolution, right? I know there's probably now billions of venture capital into it. Super want it to work out. It would be great for me if quantum technology and quantum science becomes this, $1 trillion commercial industry. Nothing I want more than that for my own personal benefit. But I'm worried about the bubble, and I'm worried about another fusion bubble, right? There was a point in the 70s where people really thought fusion was right around the corner. When that bubble burst, they canceled tokamaks all over the world, right? And then there's only like 2 or 3 left that are big enough to really do real research. Same thing with quantum. I'm really worried. There's been this huge glut of investment in quantum science and technology in terms of actually commercializing it. If it doesn't happen pretty soon, I think that interest is going to go away, and we're going to go through another 10 or 20 or 30 years of doldrums if we're not careful.
I doubt it for the reason of the development of AI. I don't see a mathematical limit other than the input data for training, which would stop the creation of AGI or superintelligence.
Yeah.
And that would mean that most of these problems would be solved very quickly, exponentially quickly, and it coincides in time with some breakthroughs in fusion. So I'm actually scared and fascinated to live in these times, but I literally think there is no 20 years.
But you yourself were just talking about Penrose and the fact that perhaps consciousness requires non-algorithmic thinking. What if this kind of invention requires non-algorithmic thinking?
Thank you for the question. So I absolutely don't believe that super intelligence will have anything to do with consciousness.
Okay.
I don't believe ever, and this is minority position in computer science, I don't believe ever any universal Turing machine or quantum computer itself, because it's discrete in a sense, qubit-based quantum computer will achieve consciousness. That's not what I think. I think that as a tool, and it's complicated, right? Because as a tool which we will consider, most people will consider conscious because it will behave as if it was conscious, it will be enormously more powerful than human brain. And that will lead to tremendous advances in many fields, including fusion, including physics. But it also will lead to tremendous problems. Is what are we doing with ourselves? Do we only have podcasts then, or and sports to do, because everything else is done by machines? So so that my perspective is both positive in a sense that I think there will be super intelligence, because I don't see the limit of the transformer technology to actually stop at some limit. Maybe physical limits. Maybe
I was about to say physical. Like energy limits. Yeah.
Well, yeah, but if it invents its own fusion and builds, it can go
fair
crazy.
Point. Yeah. Okay.
But that is independent of the consciousness.
Okay. Okay.
So, and I hope, and this is again, you hope for it, right? You hope that there is no consciousness, because otherwise, what is the point of being human, and why there should be any humans, right? If there is a super intelligence.
So I never understand that. I mean, people are always trying to figure out why humans are more conscious than animals. I'm not always certain why we're always so obsessed with that. Like, why do we think that because other things are conscious, that makes us less special?
I don't think we are not special. I believe we are very special. So that's not my position. I think that as we treat dogs well, but ants not that well, even though dogs are conscious a little bit less than us, for example, like abstract thinking, and ants are probably also somewhat conscious, but very much less than dogs. If there was a super intelligence, I don't see the reason why that super intelligence would treat us well. We'll be like pets, That would be nice of them to treat us well. But
so
why
I
would
tell
they?
all of my students when I train them, for the record, that you should have at least 2 or 3 skills that the robot overlords need. They still don't have very good hearing and fingers and vision and coordination. So they're still going to need people to like crawl into little places and fix things
For the next 5 years. 10.
Yeah,
maybe?
You think so? So I wonder if I wonder whether this complex system is going to be able to yield to this kind of algorithmic thinking, or whether complex systems to make progress, to figure out how to make progress in a system where you have sort of mixing between the micro scale and the macro scale and all the scales in between, whether you actually need intuition. And whether intuition is something that we cannot have without consciousness.
Yes, so exactly. So that's our hope, that the consciousness is non-computational and therefore cannot be simulated. That doesn't stop the super intelligence to be super intelligent, not super sentient, right?
Yeah.
Not sentient, super intelligent in a sense that it can infer from a set of not even set of rules, of rules which it itself created, things which we don't know, correlate things, right, without understanding them.
No, I recognize I have some hope that complexity, that consciousness is uniquely suited for a certain kind of complexity, right? We had a colleague come and talk about AI, right? And he talked about how, I don't know, so you have a large language model. How many words do you need to train it on? 1 trillion, 100 trillion, some huge number, right? A child by age 3 has heard 100,000 words, and in many ways can do things that these large language models still can't. Sure, they don't know anything about how to answer sort of arcane questions of trivia by correlating and combing, but they could formulate. There's certain kinds of things they're much better at, right?
But
like telling true from false.
Yes, but that's assuming that we only have large language models. We have other models.
No, fair point.
We have vision models. There will be a mix of models which simulate our senses, our perception, better than us. And I don't see a stop of it. I just don't know if it will lead to utopia or dystopia. That's the question. Okay. My sense is it will be a utopia with elements of dystopia. So everybody will be free to do whatever they want forever with any limits. There will be no food shortages, no energy shortages, nothing. But what will be the point? Like, many people will lose motivation to live, the meaning of life, because they found it in work, in intellectual pursuits. Like, in the same sense, like, we still play chess, even though we have absolutely no chance to win with a machine. there are still competitions on chess because we like it. There will be artists. The music will be better when done by AI, but there will be still musicians. Like when I invite you to my concert of The Blankets. The Blankets is, by the way, a band advertising here, which is I'm part of. It's a cover band. That's why they were called The Blankets. Yeah. The performance will be, such that some people probably should come with earplugs, but still it will be fun because it's done by human, not a perfect robot who is doing it perfectly. We cannot even imagine that such a perfectness in humans. But that will not be satisfying to everybody. That's not enough.
So I take the point, but to try to loop back to something we were talking about then is, so I think knowledge is actually like art and these other things, and that what I really mean when I say knowledge, it requires uncertainty and incompleteness to have meaning. And so I still think that people will be motivated by knowledge. I think that is satisfying in this way, and I'm not as hot as you are for the fact that the computers are going to be able to generate what I'm calling knowledge, right? They will be able to correlate things, and those things we may be able to infer. They may trigger us to create knowledge, but I guess I'm skeptical. There's nothing more than I want than fusion, right? My fantasy, right, is I want a fusion torch, because then everything you throw out, you throw into the fusion torch, it separates it into its constituent atoms. And so you just have piles of the raw atoms from which you can then synthesize with the fusion energy materials tailored for your application. Obviously, want fusion. You really think that the AI is going to help us get there?
I think, and it will be soon. I think so, and it will be soon. And not only, well, that's what I think. Not only that, in terms of knowledge, it depends how you define it. So if you define knowledge as understanding of something, then computers will never understand anything, because that requires sentience. But if you mean by knowledge formulating a new law of nature that is undetected because of the amount of data you would need to process to detect it, like for example explain inflation or something like this from background radiation, right? So something like this, which is a form of knowledge, I think will be generated. And we see it, for example, in alpha fold tree. We now know how to fold proteins, and that's a new knowledge. This protein has specific applications. That is a form of new knowledge absolutely generated by AI.
So, do you know much about the AlphaFold? Because I don't know much, and I would have some questions if you knew something.
I know a limited. Well, so
let's try it.
Sure.
Yeah. Today. So again, excited they got the Nobel Prize. Think this is a really cool technique. So I thought I had read a claim, I think in Quantum Magazine, was that the AlphaFold was really good at solving these problems, but it still in some sense was a toy model, in that you then couldn't go back and actually measure these things the way that you might naively assume.
Mm-hmm. Yeah, so you depends when you read it. So there was a version of AlphaFold which was limited modeling of the folding of proteins, because it didn't include, and I forgot the term, there is small elements which hold the proteins together in some bridges. I forgot the term, and it didn't model them. So the approximation it came up with was not necessarily that useful. But the newer model actually solves it, and there is now a run on. There's basically as many startups as in LLMs using AlphaFold to solve all kinds of problems. Right. Like cancer will be like, for example, I believe that if we progress at the speed we're progressing, we will solve cancer very soon.
Nice.
Really, like 5-10 years. Maybe clinical trials, maybe safety trials, and so on will take time. But we'll have proteins that help with it very soon. And so there is, in this sense, I think it generates a new knowledge. There is also some evidence that even large language models, which are kind of dumb, right? They just correlate data, even with this fake reasoning on top of them, they can, because of the vastness of the correlations they create, they can discover something in this field and then another field, and then come up with a new thing thanks to this connection, which would never happen in a structure of academia when people are in their silos, but not necessarily negative. It's like you don't read many biology papers in physics. Why would you, right?
And this is something I remember being a young scientist so frustrated with how siloed it was, but now I understand there's only a finite amount of time in my lifetime.
Yeah.
Right? If I want to make progress, so right now I'm working on analog quantum computing. I sort of call it the quantum abacus, right? It really turns out that if you had, quantum particles just even in one dimension, and looking at if you can manipulate these atoms, what kinds of computations can you do just by manipulating atoms on a line? Turns out this problem, it's the kind of math physics problem I like, where you say, here is the basic rules, now play out all the special cases. Figure out how many different ways there are to do this. And so I'm in the process of categorizing this right now. Super fun problem. And again, it's a way of sort of categorizing within a class of experimentally realizable one-dimensional quantum systems. What are all the possible combinatorial computation, quantum abacuses you could make, right? And so this kind of science I find exciting. I'm trying to remember. I apologize. I can't remember what I was bouncing off of that you just said. I apologize.
No, but you are getting to a very interesting thing because I've never even heard about analog quantum computers. So let's go there actually.
Yeah. Okay.
So what is the difference?
So instead of the idea of most quantum computing right now is still to make a universal quantum computer in the same model of a universal classical computer a la von Neumann, right? Where we break everything into ones and zeros and everything is into gates. If we have a complete set of gates, then we can do all possible computations. That sort of idea of creating a computer that then, because it is universal, could then, using quantum systems, maybe do all classical algorithms, but maybe faster, solve other problems, right? Have much better scaling, right? So that's the standard model. I'm not trying to make a universal quantum computer. I'm trying to make a something that could. So the most classic example of these kinds of things are already done all the time, where we want to study a solid state system of electrons in a lattice that maybe has defects because we're trying to understand high temperature superconductivity. So we make a simulation with ultra cold atoms in lattices and hope that we can sort of engineer an effective theory here where we can control the system that will allow us to understand that. So that's called quantum simulation, and in some sense that's the most basic form of an analog quantum computer. People have other proposals. Again, there are quantum electrodynamics calculations we can't do, but if we can simulate them with similar systems with atoms and photons and we can control well, maybe we can do that. So that's a kind of. There's other ones too, though. I'm interested in, there are certain combinatorics problems that it's really hard to do. They scale in a factorial or exponential way, and of course we would rather be able to do some of these math problems. One of the most famous ones is like the Ramsey problem, where it's if you have a cluster of people, how many people in the cluster know each other? Do you know the Ramsey problem?
No.
I'd have to go into detail to really get it, but it's basically a simple combinatorics problem where we know the answer for 3, we know the answer for groups of 4, for 5, or I think maybe 5 we don't know, and 6 it's just beyond any possible.
So it's in the group theory.
Combinatoric group theory, right? So there are really hard problems there, and so I want to try to come up with quantum systems that can do those combinatorics in linear or at least polynomial time.
That's brilliant. So basically, that's very interesting. So basically, instead of waiting for ever for a quantum computer with enough qubits, you can create a specialized analog quantum computer which does that particular problem.
Yes, that's right.
Very interesting. And you can reduce because it's quantum, you can reduce the complexity from non-polynomial NP to polynomial potentially.
The cases that are well known are that the determinant of a matrix, which typically goes as the cube of the number of elements of the matrix, or the permanent of a matrix, those are really easy to do because those are embedded in both the statistics of bosons and fermions. So those are like really obvious ones. So then it's to see how creative we can get. What interesting problems can we solve this way?
Can you create an analog computer for factorization?
Well, of course, that's absolutely one of the dreams, right? Yeah, is to try to do that.
So don't tell anybody, because then you can
Yeah.
break into any system.
Right now, I still need as many particles as the number I want to factorize to be distinguishable.
Oh, okay.
That's
well, it's not that bad, right? The
pretty
particles,
bad. It's pretty
because
bad.
you have to keep them.
You have to keep track of them.
You cannot have the coherence in this system.
Yeah.
You mean?
Yeah,
Okay,
yeah.
that's pretty bad.
Yeah, it's pretty
I
bad.
thought like, oh, what is the problem of having millions of atoms?
But I also need to keep track of individual ones. So yeah.
Yeah. So it's not like that we, for factorization of RSA 2048, we need 2048 qubits, and that's it, right?
Yeah, yeah,
it's
yeah.
worse than that.
Yeah, yeah,
I see.
yeah,
I
yeah.
see.
So.
Well, anyways, don't break it, because I have some bitcoins. So
Okay.
if they break it, Bitcoin is
that's
zero.
right. Yeah,
For everybody should be aware of that.
Yeah,
If there is ever a quantum computer that can break
yeah.
Bitcoin encryption, then either we have a quantum encrypted Bitcoin, or Bitcoin is worth zero.
That's right. That's right.
We'll see what happens with this. So yeah, this is really interesting. And can you speak more about the symmetry? Because my understanding of the word symmetry is very limited. I think about symmetry in space, so rotational, transitional, translational symmetry, and maybe symmetry is more general, like a arrow of time symmetry, which is the most controversial, since as far as I understand doesn't exist in quantum physics, right? It's not required. But what symmetry do you work on?
Sure. So as you were describing geometrical symmetries, when one is doing math, then one can talk more generally about the symmetry of an equation. For example, even if you have the quadratic equation gives you the two roots of the quadratic of a quadratic polynomial, you can think of those two roots as like they're exchangeable. So the quadratic equation has a kind of symmetry between the roots that is actually how symmetry was invented by Galois, to try to figure out when could you solve and to prove that you can't solve the quintic equation. That's actually a group theory result saying the quintic equation doesn't ever have enough symmetry to where you can come up with an algebraic solution to it, whereas the quartic, the cubic, and the quadratic you can. So generally it's not just the symmetry of geometry, it's the symmetry of equations, and those equations could be built on spaces like configuration space or phase space or the Hilbert space. And so I use in quantum mechanics, when I have symmetry, I can represent this symmetry in my model, and that allows me to turn what would have to be numerical analysis or calculus or some other kind of analysis into algebra, and to turn it into something that I can really do computations with a well-defined convergence. So that is one thing to say about symmetry. The other thing I like to say about symmetry, though, so the first person in some sense who really looked at symmetry was Euclid, and again was doing geometrical right. But if you look at Euclid's 13 books, in some sense, the whole point of these 13 books of classical geometry, again, starting with 5 definitions and 5 axioms, is to get to the final result, which is that in 3 dimensions, there are exactly 5 Platonic solids. And the dodecahedron, the cube, the tetrahedron, the icosahedron, and the octahedron. And it turns out this result, right, every dimension has a certain number of these perfect shapes where every face, every edge, every vertex is similar. But it's 5 in 3 dimensions, and it's 6 in 4 dimensions. Or in 3 dimensions, there's exactly 230 kinds of crystals. Exactly 230 ways, not to like physical crystals, but crystal symmetries. And this was discovered in the late 19th century, and now we've discovered a crystal with all 230 of those patterns. So this is a kind of scientific discovery that I think is underrepresented in popular discourse, where you say, okay, I will start with some axioms and then deduce what are all the possible cases. And symmetry gives you one of the main tools for this, is it says, I'm going to assume certain symmetries, or assume that a certain kind of symmetry is present, and then deduce all possible symmetries or all possible cases. And then it turns out nature tends to explore every possibility. right? And then eventually somebody shows up and says, oh, well, there's different kinds of crystals. There's quasi-crystals, which are sort of like a three-dimensional projection of a higher dimensional crystal. Well, and then we find those, right? Penrose was the one who proposed quasi-crystals. And when Dan Shechtman in the 80s took this measurement of this spectra and said the only way this makes sense is if this has some tenfold symmetry that's not supposed to be allowed in 3 dimensions, it turned out that was the quasi-crystals that Penrose and others had hypothesized should exist, 30 years before.
How is that possible that the upper dimension in mathematics are mapped to the 3-dimensional crystals?
Yeah. How is it? I mean, because we may have, in some sense, it's no more mystifying than I said before, right? Where you have an equation. To solve the equation, I'm going to go to the complex numbers, even though in the end, the equation represents reality and my answer is going to be real. Right? So in some sense, we go to this higher dimension because there are degrees of freedom, which if we hypothesize, it somehow must capture the dynamics that are taking place in some other correlation space that is different from the physical space.
I think I understood something now, that I'm actually using symmetry and without knowing it. So do you know the story of quaternions?
Yeah.
This is something which is used in computer graphics and very much, right? So I will tell it to the audience. I love this story. So Hamilton in mid-19th century was trying to see whether he can extend the complex numbers to the third dimension, right? It seemed natural. We are in 3-dimensional space, but it didn't work, right? You cannot do that. There is not the numbers don't add up. They don't stay within maybe you would say within a circular group, right?
Yeah.
But if you and then supposedly he was sitting with his son, and the son during dinner asked, "Why don't you do it in 4 dimension?" That's what I heard. Might be anecdotal, and he did that, and he discovered quaternions. So quaternions are basically 4-dimensional complex numbers, right? Kind of, fun thing, but useless. Also, we thought. And then in 1960s and 70s, we were flying Apollo to the moon and so on, Apollo mission. In 1980s, we have the computer graphics appearing, maybe a little bit earlier. And what we have a problem in this Apollo missions and computer graphics, which is called the gimbal lock, right? We represent rotations in 3 Eulers as 3 Euler angles around 3 axes, but we can get to a situation when 2 axes align, and you cannot do the rotation anymore. It actually led to a very serious accident, or almost accident, in Apollo mission, right? So someone noticed that quaternions can be translated, thought about as a representation of rotation on a hypersphere of a normalized quaternion vector, right? So, and it became solved. So the problem is the rotation in 3D space, which is represented as a point on a hypersphere in 4D space. It's exactly the example where you say that the math reduces itself naturally into 3 dimensions, but I think this is an example of application of symmetry in math.
Absolutely. I mean, it is a critical application, right? Where Hamilton was not forgotten until Apollo. This discovery of the quaternions both opened the door to recognizing that there were different kinds of mathematical structures than just the commutative algebra we learn in elementary school or middle school or high school, right? There are these matrix algebras that are non-commutative that we need to describe rotations. That ended up being wildly influential. And but this actually goes all the way back to what we were talking about in the first place, because the Kimball lock is literally the same math as when I try to make, it's a higher dimensional version of it, of when I try to say I make a projection of the sphere and my pole is mapped to a whole line. That's a terrible coordinate system, and that's the problem with the Kimball lock, right? You're just using the wrong coordinate system, but if you actually go to 3 dimensions, in the case of the globe, there's no problem with your coordinate system. It's really easy to embed it there. So it actually is even the same metaphor we were using earlier in the podcast.
Mm-hmm. And then there must be something which I don't know about the the reduction of dimensionality by 1, which solves a lot of issues.
Yeah, or I would even say, or extension of dimension by 1 is enough to solve a lot of problems.
Or
right?
this, you can look at it this way.
That's a key tool, for example, in my particular work. If you can extend a group by a circle, or I'm speaking a little colloquially, but if you could have a group and you say, okay, but what if it's just a group up to a circle? Then it turns out that's what you need to describe symmetry in quantum mechanics, because quantum mechanics has this extra degree of freedom called the phase, which is basically just like your angle in the complex plane. So that's just an extra circle degree of freedom that you have to put into the math and you have to account for if you want to really think about, it's not symmetry, it's symmetry up to a circle. So.
Do you think this might be, if you want to go there, do you think this might be the reason why string theory came about? Because it seems like basically when you have a problem, just add some dimensions and math, it becomes flexible enough.
Yeah, absolutely. Yeah, no, I mean, this is, I think the first time this happened, well, okay, it's not the first time it happens because we've already talked about Hamilton, right? But Kaluza-Klein was people who went up and De Sitter went up to 5 dimensions to see if they could solve some problems in unifying quantum mechanics and gravity. And then we found out we could go up, if we went up to 10 dimensions, maybe we could find something that included more of the standard model, right? People have been doing this absolutely for a long time, is we assume a higher symmetry and then we propose a mechanism for how that symmetry is broken in reality. Yeah, so that is, and I'll even say there is a famous Russian physicist, Lev Landau, whose life story is a story that somebody ought to make a picture of that thing. I don't know if you have ever heard of Lev Landau or know his...
I've heard about him, but tell the story.
My favorite. So amazing physicist, had his own school, was notoriously unpleasant, but really an amazing thing. And one of the things he figured out is that you could understand a whole host of phenomena using this method of symmetry breaking, include phase transitions in both classical and quantum systems. And up until the 90s, we thought every single phase transition in a physical system was an example of Landau's symmetry breaking. We now know there's something called topologically ordered materials, and there's actually a new class out there. But again, what happened to him this, one of the greatest minds of the 20th centuries was in a car accident in the maybe 57 in Soviet Russia, and had a terrible brain injury. And this person, not part of the party, not part of the whole apparatus, the entire Soviet Union worked to try to save this guy's brain, right? But he came out of it, and they did save his life. It was terrible, traumatic injuries. They saved his life, but this is a story, but it didn't heal his brain, right? And so this is the story of one of the greatest thinkers in physics of all time, actually having the head trauma. Like every single time I get on my bike, my wife sort of gives me a Lev Landau look, like, don't you Lev Landau this, right?
Well, we have. It would be interesting if. No, actually, I will cut that. This is okay. This was too dark, too dark of a joke. So it only happens. These things happen in the Soviet Union. That's I come from communist country, so. But I'm wondering because we made like a full circle through math and then back to physics, which is very interesting. I am still wondering if you think on a philosophical level whether let's start with the beginning. So we already discussed like your interpretation of something combination of information theory and shut up and calculate. But do you think that math is discovered or it is invented, meaning it exists ontologically or it is epistemologically?
Yeah, I mean, those are the two big schools. I will just mention there's also the Brouwer school of the intuitionist version of math, of Brouwer and Poincaré. And I don't know enough about that, and so I almost want to pick that third option and hope for the mystery. I mean, I think that, and I don't want to be tiresome, but in some sense, I still like the chart analogy. And that if I choose my axiom and definitions, then certainly the things that one deduces from that are inevitable, right? So when I say, is math created or discovered, invented or discovered, to me, in some sense, what discovered means is that there are inevitable logical consequences that may not be obvious, but are decidable within an axiomatic framework.
Which would mean it is discovered, right? Would you say that is it in this Well, it depends. What we mean by discovery, like a new land, discovery, it exists, but you discover that land because it's inevitable consequence. So you think the math is never invented. No new structure ever exists separately from other structures. Like imagine a guy in, there was this famous mathematician in India who, I'm trying to remember his name. Yeah, exactly. Right, who discovered a lot of mathematics by himself. Yet, well, we could say he invented it, right? Because he didn't have a background in it. He just did it completely by himself. Because what I'm going to, I don't mean like the classic Platonic definition whether it exists. I'm going to, if the math is discovered and not invented, then there is a greater somewhat chance that math is related to reality. If the math is invented, that would claim we are inventing reality, which you can also make a claim like this. But for me, math exists outside. Well, the question is, if we didn't exist, would math exist? If it would, then it is discovered.
So the physical, so what Eugene Wigner called the unreasonable effectiveness of mathematics and the natural sciences, right? This notion, I mean, so it's in some sense related to this question: created or invented? Is this something that we project onto the universe? Is it something that emerges from the universe? Is it something that underlies the universe? What role is this in math? I will say I don't know what the answer to this question is. I know I'm unsatisfied. Like, I enjoy Sean Carroll very much. The biggest gap in his big picture book I still thought was his throw-off sentences like, and math is emergent too, right? Math is emergent too? That's how I read what he said. Like, this is a question that I'm comfortable saying that in order for me to interpret the world, I have to use logic, and logic then, logic plus a few definitions gives me math, right?
But that's your process of discovery, not invention.
So if I say I have to project the world onto a logical basis of yes-no questions, then I'm not inventing yes-no, but I am inventing the questions.
Yeah, as if you invented a ship to go to America from Europe, but it is still discovery. So it's different than assuming that our brain creates a new math. So the math landscape is limited or finite, and it is expanding with our brain's inventions, like creation, as opposed to discover like a new area in a game which is behind the fall.
So I am certainly on this second side, closer to discovered than created. What I keep trying to finesse is again this information perspective, which is that what I recognize is that the process of interrogating the world around me, that is a creative process, that is an invented process, without which I can't do any discovery. And so I want to somehow not choose. I want to say that these two things are two sides. These are complementary in some way. That I have to, again, and when I say, like, maybe I project it onto two things, or I project it onto three things, or I project it onto a 17-fold symmetry, I have to ask the question that projects it onto a real line, projects it onto a quaternion, right? But I have to ask that question, and then once I make that ask, I tap into this logical structure that is bigger than my brain.
Mm-hmm. I think it's still compatible with discovery, because basically what you are claiming is like the physical discoveries. We didn't know about the existence of background radiation. How is it correctly called? I'm not using it. Background radiation. I mean from the Big
cosmic
Bang.
microwave
Background radiation, right? It did exist. Yeah. We were very creative to discover it and then describe it, but it did exist independently, whether we would find it or not. So maybe this is a similar process to in mathematics, that it already exists. It was just not yet discovered with the creativity of a human brain?
Yeah, I want to try to say something even more sort of information theoretic about I had to actually have a detector that could click or not click. In order for me to detect, one of these microwave photons, I had to have a detector that made that binary distinction between hit, not hit.
And that is the invention.
And that is the invention.
That's an
part.
interesting.
And it's not even it is literally that moment, which again ties back to our discussions of quantum measurements, right? Like what happens at that instant. So that is to me a really important moment. Yeah.
So related to that, the philosophical question: is there reality? Do we access the reality of the physical world in any way? Like, maybe this is obvious, for some people it's not. There are views that we look at the interface of the reality and never at the reality. So
so of course an easy dodge is to say, well, that's a metaphysical question and I'm a physicist. I won't make that dodge, right? But I will just say we can ask ourselves, what are the stakes of this question? So if I'm trying to be a real sort of hardcore positivist materialist, then what am I measuring? What am I observing? What's relevant here, right? What am I actually trying to claim? I definitely see correlations between observations, right? That is, I think, whether I even go all the way back to the qualia that my brain senses, right? Whatever consciousness is, I have correlations between sensations. That is true, right? That now, how much of that is the measurement apparatus and how much of that is reality? That is an important question philosophically, but scientifically, now I'm going to try to make quantitative and qualitative observations about those correlations. So I end up being a materialist. I end up believing in atoms, right? I end up believing in atoms because I find that while that is a metaphysical stance, but I find that I can move forward easier as a scientist by making that metaphysical stance. So it is really almost a utilitarian argument, not something more satisfying.
I find it fascinating. So I initially always thought that I'm perceiving the part of reality through my senses, and that reality is real. That reality represents part of the real. So, for example, a spectrum of electromagnetic field, I see that part. That's real, right? That's real. The rest is also real. Can't perceive it, but I can get a phone, and phone shows me a IR light, which I don't see, right? Things like that. I'm no longer that sure because of the quantum physics what I'm actually seeing, right? So in quantum physics, I perceive that reality and it's becoming because I'm perceiving it. That's the first problem. Mm-hmm. So what is the underlying reality if there is no physical representation of a wave function? And the second thing is that if there is a relationship between mathematics, strong relationship mapping between mathematics and physics, then maybe the mathematical reality is much more real. And the physics is almost, like some people say that consciousness is a side effect of operations of a brain, which I don't believe, but they say it. Physical world is a side effect of mathematics of that. Yeah. What do you think? This is
I am actually sympathetic to both of those. I have myself claimed that consciousness is an epiphenomena, not a phenomena, right? And similarly, I think I even tried to move towards this earlier when I was trying to say, right, when I just think about quantum mechanics from math, then it makes sense, and anything that I want to describe that I can measure, I can usually figure that out. It's when I try to think about it first from physics that it's a lot harder. And often people can do that, and there's again, I'm a mathematical physicist. There are experimentalists who start there and work the other way, but for me, that's how my approach to it. And that does resolve, that is enough. That feels almost ontological. However, I really do think the negotiation between the math and the observation and the physical reality and the qualia, I think that's information theory, right? I think that's where I feel like whatever is reality is created. Woo woo.
That's fine. You know, I have no scientific image to protect. I can say anything you want, so don't feel bad about it. And going philosophical, you know, 2,000 years of philosophy was worth something. We don't need to be so grounded, right, all the time. I'm never convinced. Maybe you can convince me, since you believe in information theory. As a computer scientist, I should be, right? I'm unconvinced by the abstraction which takes from reality and goes to anything like relation. The reality is really relational. The reality is really information. This abstraction is, I understand it on an intellectual level, it's just unconvincing, unsatisfying, and frustrating in a sense that that's the limit of knowledge. So convince me that it's better to look at the world from information theory perspective.
Okay, right. So I mean, I think I'm glad you used the word relational. I was looking for that word earlier. That it really is the right way to try to think about this. Is if I was going to try to claim this to you, I would say that because we are finite and our senses are finite, every measurement instrument is finite. The way we interact with the universe is automatically like a coarse graining, right? We're only interacting with it at a certain part of a certain scale, right? And so we really only can, our measurements in some sense discretize the universe in the finiteness of the measurement process. We're just taking little chunks. And so that's the only way we can interact with the world. And the best way to describe the correlations between little chunks of the universe, the thing that presumes that is the most predictive with making the fewest assumptions is information theory. So it is an Occam's razor. It is a minimalist interpretation of things. And so I recognize it is not satisfying, but if I'm trying to be cautious, and again, I really believe that as a scientist, we shouldn't all hold this opinion, because I really believe sometimes science progresses with false ontological models, right? Like sometimes people are wrong about the underlying thing, like Maxwell and vortices of ether. If he needed that to get to Maxwell's equations, even though that was totally false, good on him. Like, I welcome you to make these kinds of things. But if I'm trying to say from a fundamental point of view, not what helps me be a good scientist, but what is the minimal interpretation of the world that is consistent with how my materialist physicalist is, information theory is all I've got, or is the best least that I've got.
Mm-hmm. Yeah. So it is again a utilitarian approach.
Yeah.
You come from the utilitarian view. You want to have that minimal, non-dogmatic, solvable view that gives you maximum that can be given without going, as you call it, woo-woo, right? Yeah. So I have exactly the opposite. I'm totally fine believing in contradictory things and knowing that they are contradictory while exploring it. You know, it's just I think it's fun. It's like
I don't think it's just fun. I actually think it's necessary. I actually think the perspective that I'm espousing is not how I do science. That's not how I do science. So it's not even I mean, I agree it's utilitarian in the sense, but I would even say it's utilitarian in the sense that I am judging the theory based on its effectiveness in a way, but it is actually not how to do science. It is only a philosophical stance that I think is, if I was going to name something science, that's the most sciencey approach. I actually don't think we make progress in science by purely scientific reasoning. I think we use intuition and guessing and feelings and luck. And that's actually how a lot of great science gets done. But if I wanted to name the most scientific theory, I would say that's what appeals to me about information theory.
Why is that? So give me an overview of information theory. Why it is specifically, why it is so...
Why does it compel to me? Okay, well, so there are, things that I like about it, and I think Claude Shannon even says this even in his first book, is let's not worry about what the message means. let's just look about, say, how compressible the message is, whether, in sort of presaging sort of Kolmogorov algorithmic complexity, sort of just thinking about the relative information of, if I have this stimulus, what other stimulus do I expect? Can I predict? Trying to find ways to quantify the correlations between observations, trying to figure out how much that can be compressed, trying to figure out what is the minimally complex system that could produce the output of those measurements. That has again, if we are trying to not project our humanity onto things, that is, in other words, there's really a hierarchy. There's data, there's information, then there's knowledge. This is not a theory of, I agree that to get up to knowledge, we may need to start making other hypotheses about ontology or and other kinds of things. But this level is where I feel there's the least overreach into it, right? Because I don't have to, it's tricky, right? Because especially in algorithmic complexity, like, how do you know you have the best algorithm to compress the data, that there isn't some better one? Oh, it turns out that's the 600th through the 9,000th digits of pi. It wasn't a random number, right? And so how do you know that doesn't exist? But even that is satisfying to me in the fact that that uncertainty itself is quantifiable within information theory.
And it is inherently relative to the observer,
yes.
Right?
Yeah.
If, just to take an extreme example, if we drop something into a black hole, are we losing that information truly or only from our perspective, if I can say that?
Well, in that particular case, we now really do think that information ends up just being deposited on the surface of the black hole. But at least that's right. That's the Hawking.
Yeah. And by the way, why the heck the surface?
Yeah.
Anybody knows why surface?
So this is
why is not volume? That's the question. Surface, not volume.
Holographic principle. Yeah. So this is not my expertise, but But somehow this has moved all the way to the orthodox wisdom of physics. So I can't say anything smarter than that.
I know that it was calculated. It was basically calculated based on some Planck scale information unit, but it's super surprising that it is surface. It's not just something about maybe the actual unit.
No, there are people who can say clever things here, and I just don't happen to be one of them. There are several. There's literally, I have heard a very clever thing that I wish I could say right now.
I don't know much about it too. I just would like to hear one day this explanation of that we are maybe a projection of a holographic. We are living on a surface of a black hole as a simulation. Well, if the underlying theory is information theory, are we living in a simulation?
Yeah, are we living in a simulation? So I always have, and this is what I think I was rebelling against a little bit in your characterization of the hypergraphs of Wolfram, is similarly when I think of simulation, again, I feel like we have to hypothesize something outside of the system to make the simulation. And so that feels, on one hand, absolutely, in the history of science, we keep realizing my village isn't the center of the world. This world isn't the center of the solar system. The solar system is in the center of the galaxy. The galaxy is not the center of the universe, etc., etc., etc. So sure, our universe is one of many universes, and perhaps of these many universes, they are all somehow simulations. But again, I still feel like we're going.
But you mean that we would require an unconscious agent to run the simulation, like God, or you mean
we would need something outside of our universe, which, by definition, which I presume would therefore would be not of our universe. And therefore, in some sense, we introduce a dualism. We may introduce some other conscious super agent. We may, at the very least, propose another layer to which we cannot interact within the rules of our universe. All of those things, those are the definitions of not science.
Well, yes, if you assume that that metaphysics, but it can be physics. It's just unknown physics, right? Like there is a region of space of a universe we know, and the region we will never know. Anything could happen there. Law of physics might not work there, right?
Yeah.
And that doesn't mean it is metaphysical. It's just unknowable. So, like maybe you've heard about the Penrose idea of cycles of time. The universes are cyclical and they collapse and recreate itself from new big bangs. To simplify it, that will never be known. Although he has some idea how to discover the reminiscence, but it's not necessarily metaphysical. That's what I wanted to say.
Yeah, no, and I take the point, right? And just because something is unknown, I shouldn't label it as metaphysics. I still feel... So again, I wonder, what is the impulse here? Right. So, and again, I may be still being too utilitarian, because I'm not really a utilitarian in terms of most of my ethical choices, but still, so if we have testable consequences and no simpler explanation, then I'm all in. If you're making testable consequences in principle that we can't test, if you're saying it is not just that I'm hypothesizing this, but I'm hypothesizing that it is in principle untestable, that's where you cross some line to me. And I begin to wonder, what is the emotional, what is the cultural motivation for this? And begin to suspect, for example, it's a drive for determinism. Or it's a drive for some other sense of meaning, that maybe if we don't have determinism, we have to find some other sense of meaning or an explanation for the lack of meaning. And there is just the cynic in me, the skeptic in me, who says, the universe doesn't owe me meaning. I'm a child of the 20th century. We make our own meaning. And the people who are looking for meaning in many worlds and simulations, in string theory, right? If you're looking for meaning there, I want to encourage us to make our own meaning. And I think that's what I like about information theory too, right? Because it really says that fundamentally, it's when I make the observations. I mean, again, I'm not saying we're creating reality, but when we make our observations, that is the most important substrate of reality, with that interaction.
I would slightly disagree with this connection of the postmodern self-meaning creation and the idea and the problem with, for example, theoretical physics, which doesn't give predictions which are testable. I think this is disconnected in a sense that first of all, I don't subscribe to the postmodern view, because I think there is an inherent hierarchy, and therefore that creates meaning in the world. Inherent hierarchy, which is unavoidable. But that's a different philosophical discussion. But regarding the theories in physics that have no predictions that are verifiable, I was always wondering, how did it get to science ever? Like, this feels like decadent end of science going,
it's always been there.
It's crazy. It was.
Oh yeah, of course.
I thought it was recent. Like, I understand. So as I see, the process was like this. First, we had experimentalist driven discoveries. We had some data, we discovered electricity, whatever, Maxwell, and so on. Then we had Einstein coming and completely theoretizing everything with zero evidence, and then everything is confirmed. So people are like, wow, you can start with math, and then you have actual reality, and it works, and it's super practical, amazing. So everybody started to theoretize. And then that led to crazy ideas, which are completely unverifiable, but everybody's saying, it's still, the math is beautiful, therefore it must exist, right? That doesn't make any sense. Why there is ever, are there other examples of theories which had no verifiable predictions and are considered
So the caloric, which was an early theory of heat, was a massless, colorless, tasteless, odorless, shapeless fluid, and that was what explained heat. Because they were trying to understand heat flow and how things, right, thermal contact, how temperatures changes. And this was literally what they hypothesized, because when they made that hypothesis, they could make a math model using partial differential equations that actually was verifiable. The ether for electromagnetism, people hypothesized the ether, and Maxwell himself said, like, okay, this is going to be something that has no mass, we can't touch it, we can't do anything. However, I can represent knots and vortices in it as fields and structures. So I see the tradition. I mean, I see that while I grew up in the 90s, string theory was was exploding. It was absorbing some of the great young minds of my generation. In my university, if you were ambitious, you wanted to join the string theory if you were an ambitious young theorist. And I, for reasons that have more to do with personal psychology than intellectual, chose not to compete in that realm. Was like, that's not the way I want to do science, is in this sort of, pardon the expression, dick swinging, right, kind of realm of how I perceived that community. And so, but it attracted a lot of funding when I was looking for jobs. The advertisements, even at like liberal arts colleges, were hiring string theory. Everybody wanted a string theorist. All the kids were into string theory. Everybody wanted a pet, at least one string theorist at their institution, because that's what they thought was happening. So, I mean, I do understand it was excessive. The excess grew out of the tremendous success of particle physics in the 20th century and the tremendous successes of this method. I mean, one way to think about it is we just got unlucky that after you get down to about 10 to the minus 15, 10 to the minus 18 meters, then it's another, 100 billion times before you get to the next structure. If there would have been more structures along there, string theory probably would have found them, and then we wouldn't be having this discussion.
But it is different than, do you give an example of ether and caloric? It's different because it was verifiable. Maybe not at the time, maybe people believed it and it was wrong. That's not what I'm saying. What we know about the string theory is it is inherently unverifiable. Well, not maybe in principle, but in any practical way, right? Because of 10 to the 500 possible solutions, because if you want to find potentially a supersymmetry, you need now what
they didn't know that at the beginning.
That's fine. You can excuse them in 1990s,
yeah.
in the second string theory revolution. Fine. And it's beautiful and it's cool.
Great math.
How do you excuse it for the last 20 years?
So my impression, though, and again, I feel bad because I was one of the people who was trying to kill string theory. I literally was speaking against it in the early 2000s, trying to say this was overblown, we've got to start changing directions. But now I feel a little bad for them, right? I do think they're on the decline. When you look out into the job ads, nobody's hiring string theory anymore. The people who are doing string theory are just the people who I think need to get more people are leaving it and moving into other fields. I believe it is. I don't think we need to kick it while it's down. I think I came here to bury string theory, not to praise it. But I now think it is dying. And now we need to
Well, I'm outside of the field. I don't understand why you would feel bad about it. The reason why I not feel bad about it is because I read the book by Lee Smolin, and it looked to me like it's not that the string theory was popular. That's fine. That there are fashions, and it might have been, and it might be the theory of everything. The problem is that everyone else was laughed at and not getting any funding, literally nothing, and that's unacceptable because you wasted billions of dollars and hundreds of brilliant minds on something which was pure math.
It's sad. So again, pure math is not without value, and some of the math they did has helped math and has helped physics in other ways. I mean, I agree with you. It was excess. I'm just saying. Again, I feel guilty because I personally felt like I was one of the people who were like, why aren't you doing important physics? You're not doing string theory. And I was like, I sort of want to do something.
Unorthodox.
Yeah, well, maybe. Yeah, I did at the time, right? Yeah, that's right.
Interesting.
So, yeah, and at the time, and of course I just was there, and suddenly it's like, wait a second. String theory, by the time I was getting my PhD, it was already second string theory revolution. It was being well developed. You had to really go specialist. Whereas when I was in the late 90s, you could make progress in quantum information theory in the afternoon. Like you could have a few hours and be like, hey, I don't think anybody's ever asked this question before. Yeah. And then it turns out within 10 years, we're making those measurements on a regular basis in the lab. That's what got exciting. So, I mean, I do feel bad because if they would have at least found supersymmetry at CERN, right? But there's whole people who've spent decades of their lives. And yes, were they at some point the oppressors and now they are the oppressed? Yes, but we shouldn't kick them now that they're down. We should show them mercy.
Well, no, I am less merciful because of potential discoveries that have not happened. What I only mean is that if 50% of funding was dedicated, 50%, that not 100%, okay, not 99%.
Oh,
not
and so we have to be careful because I actually don't know. I mean, like, and we shouldn't. I mean, 90%. First off, string theorists are cheap. Right, particle experiments, expensive. String theorists are cheap. I mean, relatively.
As you build a hadron collider.
Yeah. So
that's a good point. So the last question, I don't want to over-exhaust you here.
Or our listeners.
Is there something fascinating which you know of, something which would be like, if I was a young physicist today, that's what I would work on?
Okay, yeah. I mean, so I've already alluded to this, but so there was a belief for ever since Lev Landau in the 1940s maybe came up with symmetry breaking, that we understood how if you had electrons in a metal or some other crystalline subject or even in some other amorphous solid, we sort of, and depending on whether it was a solid, a liquid, or a gas, or maybe you could turn up a field and it would change from a magnet to not a magnet or something like that. We had a theory for all of that was based on symmetry breaking. And how whenever you made a transition from one phase of matter to the other, there was symmetry breaking. In the 80s, they started making some weird measurements of systems where like the conductivity had like weird plateaus. In other words, like there's sort of a discreteness in a material that we didn't expect. The integer quantum Hall effect, the fractional quantum Hall effect. At first, people thought, oh, this is going to be the secret to high-temperature superconductivity. We still don't know the origin, the materialist physical origins of high-temperature superconductivity. We still can't sort of give it a coherent and complete explanation. But we now at least understand there's a whole other class of matters that are called topologically ordered materials that we are just beginning to understand that these kinds of properties. And it's funny because we've been talking about locality. So the whole idea of symmetry, the whole precept of symmetry breaking sort of was based on if there were any correlations between the electrons in the system would necessarily be local. But now, if you have a topologically ordered material, the correlations between the constituents in that state of matter have long-range entanglement, and that long-range entanglement is characterized by topological, global properties of the system, not by the local properties of the system. And we're still just beginning to figure out we can make some of these materials, we can measure some of these materials. The theory is being developed. Chao Guang-Wen will get a Nobel Prize. Please, Wen, ready to talk more about this. But yeah, Wen will get a Nobel Prize, in my opinion. That is where I would steer a young theorist who wants to do the coolest math in quantum mechanics and quantum field theory.
Is it part of a solid state physics that would be called, because I heard that there is a revolution in solid state, which I don't know much about.
Yeah,
so that would be considered...
Absolutely. Solid state, condensed matter, I use those two words pretty much interchangeably.
Very cool.
So this is absolutely it. Topologically ordered materials related to something called topological insulators. Topological insulators are insulators on the bulk of the material, but currents can flow freely on the edge. It's related to topological quantum computing because we believe that in a topologically ordered material, the things that carry the charge, that carry the currents are actually anyons. They have a sort of topological exchange statistics that are robust enough to do universal quantum computation. So, I mean, this is, there was a simulation on, these kinds of topological materials have been simulated on one of the biggest superconducting quantum computers, right? So we have some confirmation that these things, just in the last year or two, we have simulations of them on a quantum system that really work. So it's, that's the field that I think is the hottest right now.
So despite the debacle, the problems with string theory and the theoretical physics, there is lots of interesting things happening in physics.
Absolutely.
I have a final anecdote. I just wanted to tell you. I'm saying it at the end because it's a little bit controversial Polish anecdote, but I like it and I think it's a good ending. So, as I said, I was not that interested in physics when I was a kid, and one reason I was thinking what happened. Well, one reason was the teacher of Russian who was turned into teacher of physics I told you about. But there was another kind of situation. So I was going by train to my school. Every day I had to wake up at 6 and go 1 hour to my school by train. And one day I was sitting in the compartments. In Poland during communism we had these like compartmental trains, not like big, but you sit in front of another person. And a completely drunk guy comes in. And I was like, oh no, the drunk guy, this will be trouble. I'm like a teenager. He sits in front of me, looks at me, and then falls asleep. And I'm like, okay, he fell asleep, that's great. And then suddenly he wakes up and exclaims, "Physics is dead!" I'm like, what happened here? And then he falls asleep again. And then after a while, like it was a long drive, he woke up and we chatted, and he was a professor of physics. And that was in 1994. So I was wondering why would he be drunk and be sad about physics being dead? But now my conclusion, maybe it was the second revolution of string theory that should be positive for him. Now my conclusion is that physics is definitely not dead. Maybe the theoretical physics is in some trouble, but the physics is still fascinating, and there is a lot of things which can happen. So hopefully people will discover new things with help of AIs and in the near future. So thank you very much for this long conversation.
Thank you.